Hello, everyone. Thank you for joining today's Deeper Talk seminar. I'm Jared Heiss, Science Director at SURF. A few quick housekeeping notes before we begin. Today's talk will be about 40 minutes, followed by 10 to 15 minutes of question and answer. You can ask questions live by raising your hand in Zoom or by using the Q&A button. This talk is being recorded and will be available on institute.surf/deeper-talks, as well as on SURF's YouTube and Vimeo channels. To receive notifications about upcoming talks, visit the Connect link at the top of the institute.surf web page. New for this and future talks, we now have a dedicated Slack channel to continue the conversation after each colloquium or to follow up later. You're welcome to ask additional questions of the speaker or engage the broader group assembled there. Our featured speaker will be available in Slack for up to 30 minutes following the talk, and we'll share the link in the chat. Now, it's my pleasure to introduce today's speaker. Dr. Brianna Mount is faculty at Black Hills State University and the lab director of the Black Hills State University Underground Campus, which is a clean room facility on the 4850-foot level of SURF. She is also the PI of the BHSU Inductively Coupled Plasma Mass Spectrometer, ICP-MS lab. Through both of these projects, she's been able to build interdisciplinary collaborations with biologists and chemists, and is a member of the Lux Zeppelin and G-STAR collaborations. I also want to mention that Professor Mount is an inaugural member of the SURF User Association Executive Committee. Furthermore, Dr. Mount was a co-convener for the Underground Facilities and Infrastructure Frontier during SNOMAS community meetings that ultimately informed the most recent U.S. Strategic Plan for High Energy Physics. Now let's get ready to explore low background counting at SURF, the Black Hills State University Underground Campus.
Hi, thank you, Jarrett, very much. And I just want to thank the SURF Institute for inviting me today. As Jarrett mentioned, I'm going to be talking about the BHSU Underground Campus, or the BHUC. I'm going to go through a little bit of history in the past, before these counters were at SURF, their history at SURF, and then where we're at right now. Sorry, let me just, there we go. So this kind of turned into be some kind of advertisement for the Black Hills, which it wasn't meant to be. But let's see. So where is my? There we go. So we have South Dakota here, and we're in the beautiful Black Hills, which famously looks like a human heart. If you zoom out from it, we're here right now in Lead, and my home institution, Black Hills State University, is in Spearfish. So BHSU is about a 30-minute drive to SURF, so it's pretty close. I may have made it 20 minutes if I was late for a cage. And so it's a wonderful location that we have here in South Dakota. So the BHUC is a user facility on the 4850-foot level of SURF. Here's a picture of it right here. This is a rendering from the construction of the BHUC. And we house high purity germanium low background counters. We also have space for biologists, and we're also open to other small scale experiments. So if you come into the BHUC from the drift, you walk in here and go around, and we have a work area here where we often have lunch or discussions, and then we have our clean room. This area right here is our gowning room, and then we have two entrances into the clean room. There's a divider line right here. One is a class 10,000 clean room that in the past has been reserved for biology use. And the second part is our class 1,000 clean room, where our low background counters are housed. I should mention funding for the original clean room and some of the amenities, like the vacuum jacketed tubing and stainless steel tubing for the nitrogen purge, was provided by the South Dakota Board of Regents and Black Hills State University. And then funds from the South Dakota Science and Technology Authority provided a reworked, updated, and safe cavern for the clean room. So just to give you a feel of the location of the BHUC on the 4850, we have two main ways that we get underground. One is via the Yates shaft, and one is the Ross shaft. I happen to be about a mile up right now on top of near the top of the Yates shaft. The Davis campus is where the historical Ray Davis experiment was housed. where the LZ experiment is and where the Majorana demonstrator was housed as well. And then across the other side, you have the Ross shaft is another way to get underground. The big, wonderful, enormous dune caverns are here in green. And then you can kind of see this little small blue cavern, and that's where the Ross campus BHUC is. It was an old drill bit repair shop, and it turns out that we've moved the contents of this clean room twice. Some detectors have been moved more, and I'll talk about that in a minute. But as far as the history of the Ross campus BHUC, this is what it looked like the first time that I saw it. We had got the funding from the Board of Regents for this clean room. We had talked to SURF and got their support with their funding as well. And I walked into this dirty cavern where the, I think they call this cribbage, it was being, the ceiling was being held up by these logs here. But it's been a pretty impressive transition. This is a GoPro that Matt Kappas had put up in the BHUC when construction was starting. So you can see already that there has been shotcrete, the spray-on concrete on the walls, and the cement floor that was already existing had been cleaned up quite a bit. Let me just push play on this. There we go. So it's just kind of a fun little video showing the different areas. So right now they're getting ready to pour the concrete for the clean room pad that the clean room will sit on. So where you walk into the BHUC right here, that has the historic concrete, but the clean room is sitting on a new pad. Over here, you'll see them working on an HVAC system to supply clean air to the clean room. And in a minute, they'll paint the clean room pad orange. So we chose orange just like the Davis campus had also previously chosen orange so that we can see dirt more easily. So that's why you'll see these wonderful bright orange floors on the clean room in the Davis and in the Ross campuses. The other kind of unique thing about this cavern is one thought for it originally was to try to make it a radon bottle. And so we applied epoxy in addition to the concrete to hopefully help stop radon from seeping in from the walk walls. So here's the clean room being constructed. You can see here the biology side door, and this is the counting clean room side door. And I think we'll just maybe skip to the end a little bit. And I'll show you some pictures of what it looked like in the end. So after walking into that cavern that just looked filthy and dirty, we got this wonderful clean room area. So this is the work area on the back side of the BHUC. What you're seeing right here is the other side of the biology room here and the counting clean room here. The BHUC biology room, this is Professor David Bergman and some of his students. What they would do is go to remote places in the lab, grab what I think looks like snot, they call it biofilms, and come and I'll do a quick analysis here at the BHUC before taking it to the BHSU campus. So that's the biology clean room. That's a class 10,000 clean room. This is the BHUC counting clean room. It's a little bit hard to take pictures because everything is so enclosed. But you can see here, these are our germanium detectors. So this is the twins, what we call Maven, Morgan, Rhyme and Reason, Mordred, Merlin, and space for future detectors. So what that looks like in real life is something like this. So you can see the twins is the dual crystal low background counter that I will talk about in a little bit, and the rest of them as well. So this is what it looks like in real life. So that was moving into the BHUC in the Ross campus. But actually, a few of these detectors existed before Sanford Lab and actually existed at a different location in Sanford Lab as well. One of the things that I mentioned about the BHUC is that it's a user facility. So we had the clean room, and then we work with different groups to install their detectors in our clean room. And so one of the strong partnerships that we've had is with Lawrence Berkeley National Lab. So for example, this is a picture of the MAVE detector that was actually first installed in the Davis campus. Also, there was a Cube detector that later became Mordred that was also installed in the Davis campus. So they were moved out when the when the BHUC was completed in late 2015. Before this, MAVE was actually housed below the Oroville Dam in California. And like I said, these are some of our collaborators at Berkeley that helped with the install of the original Ross campus. So we've got, we've got Kevin Lesko here, Kelsey Oliver Mallory, and then Keenan Thomas here. And I particularly like this picture. I can't remember now if this is Morgan or Maeve, but here they are with the first install. You can see the crystal here with its copper box, and then the lead shielding that is being built around it. So the Berkeley low background counting started with Al Smith over 60 years ago, and these are pictures of Al Smith. So here he is loading a sample. Here he is with another lead castle. And right now, the Berkeley Low Background Facility is currently directed by Kevin Lesko. And there are 5 detectors underground that they control: Maeve, Morgan, Mordred, which is in partnership with University of South Dakota, Merlin, and the Twins, which is also in partnership with UC Santa Barbara. I love seeing these. Kevin sent me these pictures, and I absolutely love seeing these, especially this one, because I think Al is grabbing a lead brick with his hands. And so right now, if anybody's done anything at SURF, we always have safety procedures that we write and that we follow very carefully. And that would not be acceptable in the safety procedures. And then Berkeley Lab is perhaps even more extreme. This is Keenan Thomas, who is at Berkeley, but is now at Livermore National Lab. And these are the current precautions versus just using your hands to work with the lead bricks. So I mentioned that some of our detectors have moved from Oroville to the Davis campus to the Ross campus. And I'm about to talk about some more moves as well. Each lead shield that we have contains about 500 lead bricks. This is about 13,000 pounds for each shield that has to be stacked by hand, brick by brick. And it's not only just the stacking of each lead shield, we also have to move the lead into the clean room and then stack it and move it from wherever it came from. And so we touch these bricks quite a bit when we're moving the lab. And so I was kind of thinking about different ways to think about 13,000 pounds. I think I might have gotten a little punchy last night when I put this slide together. I couldn't think, I didn't feel like I was being very creative. So this is actually Chat GPT results for I asked them for 13,000 pounds equivalent slightly silly. And so about 13,000 pounds is about 1.5 adult elephants, 4 average giraffes, 13 cows, and I did not put these parentheses in, that was the AI, or 1 very judgmental T-Rex toe, 65 adults, 2,600 newborn babies, 1 physics class right after finals week is very true, I think. And then we have the South Dakota reference with a car made of snow or a very, very dense bison. So a little bit silly, but we have moved these bricks, and it is a considerable amount of effort. So we had the BHUC, it was constructed, and then we moved several detectors in. So this is just a table that shows the year, how many samples we did over all of our detectors, and some notes about when we started each detector. So our first detector at the Ross campus was Morgan, and it started samples in January 2016, followed by Maeve. Solo was actually a detector that was moved out of the Sudan Underground Lab in 2016 to SURF. And then Mordred started samples later that fall as well. So from 2015 to 2020, we counted about 300 samples, and this does not, and that, in addition to the samples, we also did background runs and calibration runs. And so these counters were almost fully subscribed for those 5 years, mainly on LZ samples. We had a very successful run of being able to look at most of the materials that went into the LZ detector. Of course, we did that with partners at Bolby Lab in Alabama and other low background counting facilities around the world, but we're very proud of that program. And then also what you're seeing here in this picture are LZ PMTs. So you can see that there were special holders made so that these PMTs could fit over the crystals. And depending on the detector, we could do 7 to 8 PMTs at a certain counting time. Our counting time is about 2 weeks. So it takes a little bit to count these samples because they are so ultra low background samples that it takes a while to gather enough gammas to be able to say much about the samples. You'll see that this graph or this table ends in 2020. So in 2020, what happened was these enormous dune caverns were going to be starting to be blasted. And so in the summer of 2020, there was a rush to leave the Ross campus, pack everything up, and kind of mothball the BHUC and take everything via motor over here to the Davis campus to a temporary location. And so in some of our information, you'll see us call this the new BHUC. So this is the Davis campus. So this is the 4850. This is where you would come down on the Yates shaft, on the Yates cage, and you would walk up to the Big X and then over and into the Davis campus. So just to kind of orient folks, this is where the Ray Davis experiment was and where LZ is currently. This is what is called the common corridor. And then this is Majorana space. So you have the Majorana demonstrator detector room here. The electroforming room, and then this whole piece right here was a machine shop for their electroformed copper. We were able to get a little bit of it to put our low background counters in. So this is where our low background counters were from 2020 until last summer. This is what it looked like. So this is the common corridor. So you would step through these doors. This is a picture from this door, I think, actually looking in this way at Morgan and Maeve, which are right here. We have the twins detector, Mordred. We have another group of collaborators from the University of Alabama and the University of Kentucky, and they have their germanium 4 detector in this room as well. So germanium 1, 2, and 3, I believe, are at the University of Alabama, and so this is what they're calling germanium 4. Another new piece for the Davis campus was Rhyme and Reason from Lawrence Livermore National Lab. So Rhyme and Reason, I will have pictures on later, but this is, in addition to the twins, this is another dual crystal in one low background shield as well. So you'll see we had to make sure that there were a lot of constraints on space and walkways. We had to make sure the Majorana folks could get their copper through here into the machine shop and out the door. We had to make sure we had room for fire hydrants or not fire hydrants, fire extinguishers and things like that. Fire hydrant would be pretty funny on the underground. And so things are really shoehorned in here. We used every little bit of space that we could. And so it is where the BHUC was located from 2020 to 2025. So during this time at the Ross and at the Davis, we have, while a lot of our focus was on the LZ experiment, we are open to doing assays for anyone in the community. And so these are some of the collaborations for which we have counted samples. So Lux and LZ, Protodune, Cupid, an interesting Livermore water sample suite that we did, Ice Cube, Legend, Nexo, Thea, Next, and right now we're working on XLZ-D cross-calibration samples. But I kind of mentioned we were shoehorned in there at the Davis, but in the summer 2025, we were able to move back to the Ross campus. So now we're home. We've got a little bit of elbow room. And this Ross campus was designed to house low background counting. So we have stations around the counting room for liquid nitrogen fills, for purge gas delivery, and electricity. So it was very exciting to get back, but it also took a little bit of work. So I think these are pictures from January 2025 or so. So you can see, if you remember the pictures from the beginning, they were bright orange and beautiful, and this is looking a little bit dingy. And you can see here, this is actually the entrance to the biology clean room. And so even the clean room itself took a little bit of scrubbing. And we could not have done this without D. Espinoza helping us underground with this cleaning. It was quite the task. Or we also, I should thank my students. So in this picture, there's Bailey May, Reagan Ray, Colby Rouse, and Katie Pedno here, and they are wiping down the soft-walled clean room that we use as a gowning room. So bad pun. So we had to get the lead out of the Davis, and this is how we did it. So we would take these carts into the clean room, unstack the lead stacks of the detector, wheel the carts into the cart wash. So this is kind of the in-between area between the dirty side outside these doors, the drift, and the common corridor side here. And so we would take these carts that had been in the clean room and unload them into what we call these mini crates. These mini crates were specially designed to hold this lead. And these are two teachers that we made do manual labor this summer, but I think they enjoyed it, and they came out with some activities that they could take back to their local high schools, I think. These are just some more pictures from Move. So I'm not sure if these are packed or going to be packed, but these are the lead crates. I guess these are going to be packed because that's too high. We had to, wrap everything in pallet wrap and keep it as clean as possible to the transition back to the Ross campus. So I mentioned that we moved this lead via the motors that are underground. So the trains, the low-keys, depending on what part of mining you're in. This is a man car, and it's kind of hard to see, but these are flat decks that have the lead crates in them. So the first detector in was Livermore's rhyme and reason detector. We have here, so you can see, it's kind of hard to see, but this detector has two crystals. So you can see the top crystal here, and then there's a bottom crystal here that's being covered with these copper rings as they're putting it in. You can see some of them being ready to be unpacked over here. And then our first Berkeley detector in was Morgan. And so you can see some of our summer RU students here, and then Doug Keat and Katie Pedno, who are enormous helps underground. And you can see the amount of lead. And so very, very, very quickly, you understand how best to stack lead so that you can pick it up easy. And I think probably the best amount of people is 4 for the lead stack. So people can be putting lead on the stack and actually placing it in teams of 2. This is Maeve. These are more RU students from the summer of 2025. And our most recent detector is Merlin. And so I kind of skipped over. So the twins are over here. You have Morgan and Maeve. This is Rhyme and Reason, the Livermore detector. This is Mordred, the detector that is a collaboration with Berkeley and University of South Dakota. And then this is Merlin. So Merlin, previous to this year, had been located at Berkeley Lab, and it had been used as a pre-screener for the LZ samples from 2015 to 2020. And now we've moved it underground as we've had space. You can see more lead bricks, and actually I'm headed underground this afternoon with Katie and Doug to hopefully finish Mordred. So hopefully that will be done today with the lead stacking, and maybe next week with the mylar wrap that we put around the detectors. So this is the layout that we have right now. So we have our detectors. This one isn't existing right now, but you can see there is space for more detectors in the future. So that was the history. So that's where we are now. Is we're back at the Ross after moving back and forth and moving each time we moved. I think we moved about 60,000 pounds of lead brick by brick. But now we're back, and all of our counters are counting except Merlin. And so I thought, maybe this is a good time to switch to a little bit of what we do and how we do it. So just a little reminder, this is why we need why do we need these assays? And two main reasons. When you're designing an experiment, you need to be able to choose your materials. So you need to know if this plastic is more low background than this plastic, or if this manufacturing technique is better than this manufacturing technique for giving us low background materials, that sort of thing. And then once you've chosen your components for something like, this is the LZ-TPC, time projection chamber, you need to know how much radioactive elements you have in all of these different little components that you're making up your TPC with to inform your background models. And so high purity germanium detectors are wonderful for this. They can perform assays for anything that will fit in a detector shield. So again, to the right here, you can see LZ PMTs that we counted. A typical counting time for low background samples is 2 weeks. So it does take a little bit, but it's also a non-destructive technique. And so you can hand me an LZ PMT and I will hand it back to you without shattering it or dissolving it, or digesting it in an acid. What these detectors actually look like is you have these crystals here. So this is where the germanium crystal is. In this case, we have copper housing for it. You'll see the dewar here, and then a cold finger keeping the crystal cold with its metal contact. And then we have a copper box in the center of these castles, and then you can see the lead on the outside. And so here are just kind of 3 different views of in this case, this is Mordred. If you're looking down into the counter, so now if you're standing up and looking down, this is what you would see. So here is the crystal housing. Here is a sample. Then we have our copper box and our lead around it. We also have, once we finish our lead stacks, we then wrap them in mylar. So that's the silvery looking aluminum that you see here. And the reason that we do that is because we're always trying to get away from radon because it's right in the middle of our decay chains. And so what we do with our detectors is we wrap them in mylar as well as we can. And then I couldn't actually find a picture that we show our purge tubing, but we have stainless steel tubing that goes from the liquid nitrogen boil off outside of our clean room. And it's fed inside our clean room. And then at each detector, we have plastic tubing that actually goes into the shield. And so that radon is actually going into the space of the shield where the crystal is. It sits right under the crystal and the cold finger within the copper and the lead box. And like I said, it is fed with liquid nitrogen boil off. This is very effective. So one thing that's not on this plot that I hope to do in the future is just by going underground, we get an increase of about 70 in sensitivity. And then these 3 traces, the blue trace is a detector at surf with no sample in it. It's just background. It doesn't have a shield, so it doesn't have any lead or copper around it, and no radon purge. The black trace is with lead, but no radon purge. And then the red is what our detector background ultimately is, which is a lead shield and radon purge. So you can see how important radon purge is, especially here underground at surf. To open one of these up, it's pretty easy. You don't have to unstack each piece of lead. These carriages, the Berkeley method, have these boxes are filled with lead, and then this handle pops them up onto rollers, and you can roll it out of the way, and then you can open. So this is the lead box right here, and then you can open the copper shield here. I apologize for this particular graphic, but I wanted to show something as clean as I could find. So this is what we're looking for with the thorium and uranium decay chains. When we report our numbers, we usually report early chain and late chain, so before and after radon, to make sure that we're in equilibrium. These are some just peaks that we're typically looking for. So the way that to read this table is we have our different components. So we have two isotopes, lead-210 and potassium-40, that only have one line each. So I just put them over here. But then we break it out into early uranium and late uranium, and early thorium and late thorium, and the different daughters for that particular portion of the decay chain. So this is what that actually looks like. So of course, each one of these energies corresponds to one of these peaks. And this is what we're looking for when we're looking at a spectra. So I think this is a typical spectra of, it looks like a metal sample because I can see cobalt-60 there. Okay, so once we put our sample in our detector and we counted for 2 weeks and we got the spectra that I showed you, we then fit these different transition lines, and we are able to get the peak area under each one of those transition lines, which then feeds into our equation for concentration. And so the other things that you need to know when finding concentration are the mass of the sample, the branching ratio, and the lifetime of the sample, how long you have counted the sample. The other thing that's a little bit harder to determine sometimes is the efficiency of it. So how many gammas are hitting your crystal out of how many that are being emitted by the sample. People do this in different ways. One of the ways that is a physical way that you can really test out, and so I like, is we have a calibration sample. And this calibration sample is called table mountain latite. And it's been well characterized. It was started by Al Smith, and it's been well characterized over the past couple of decades via other germanium detectors, but then also via ICP-MS. And so we use a ratio method to back out the efficiency for, using this calibration sample, since we know well the uranium, thorium, potassium content of that sample. It does have limitations to use this sample. So we have to have samples that are a little bit more uniform. So we tend to count samples in Petri dishes or in Marinelli beaker like you see here. And it's harder to do odd sample geometries. So, and the other thing is, if you get a sample that's too dense, you can have some problems with self-attenuating samples as well. So it's not perfect, but it's a very good sanity check. We're also developing some robust GEONT4 simulations to determine efficiency as well. So I personally think you should do both. These are the current and planned germanium detectors at the BHUC. So we have Morgan, Maeve, Mordred, all BF, and then Mordred with the USD as well. 2 P types and an N type. And then you can see the sensitivity. So this is the sensitivity to uranium, sensitivity to thorium, and millibecquerel per kilogram. Germanium-4 was operational at one time, but is not at the moment. So we have that value is to be determined. Similar with Merlin, it's not quite built yet, so we don't have a sensitivity listed for that. The twins detector, and then rhyme and reason as well. So those are the 2 crystals in one castle, and just by having more mass, I think will be more sensitive. But then also the plan is to do coincidence counting with those detectors as well, to hopefully get even better sensitivity. So we're excited to see those 2 detectors when they come online. Both of them are actually taking data, but we're doing calibrations and working on the best way to do data analysis with those 2 detectors right now. These limits are sensitivities for about a 1 or 2 kilogram sample for about 2 weeks sample time. So these are just some shiny pictures. So Mordred's here on the left, Maeve and Morgan are on the right. This is a bird's eye view of the twins with a deconstructed shield. So you can see the two crystals here. This is the completed shield without the mylar yet. So you can see the two dewars here. The twins are also special because this particular crystal is connected to this dewar, which is on a track that can slide back and forth. So this crystal here can go in or far like it is right now to accommodate different sizes of samples. Other collaborators underground, I mentioned germanium 4 with University of Alabama, University of Kentucky. This was its location in the Ross campus. We hope it makes it back there soon. Rhyme and Reason is at Livermore, and here you can see the two crystals in one lead shield. Here they have, this is a lead shield, but it's a monolithic lead shield that they've purchased commercially. We also have pre-screening partners at Above Ground Labs who have sent me some slides. Thank you very much. So this is the UCLA Grizzly high purity germanium detector run by Alvin Kamaha, and it is at the UCLA campus. You can see a feature here is she has some muon vetoing panels around her detector. And the plan is if we're unsure about a particular sample, if we're not sure how hot it is, we can send it to Alvin or to Jürgen in the next slide to determine if it's worthwhile to spend the precious underground time counting the sample. This is Jürgen Rickenbacher's rabbit at South Dakota School of Mines, also a very close institution to serve. Some features for rabbit is, again, it's above ground, so easy to access. And then he also has quite a large sample space as well to accommodate larger samples. So I'm almost done here, but I wanted to talk about the people because nothing ever works well without people. In particular, this is the local team. So this is a little confusing where I put their names, but this is Doug Pete. Nothing at the BHUC could work without Doug. It just couldn't. He's just been absolutely amazing. He started working with us, I think, in about 2020 or so. And then this is Katie. Also, nothing would be running smoothly at the BHUC without Katie either. She's been working since, well, she was an undergraduate at Black Hills State, and she's been working as a post-bac for me since last summer. And these two were absolutely phenomenal and instrumental in data analysis and also moving the BHUC this last summer. Also, a new recent addition to our group is Harkirat Riyat, and he's currently actually at Berkeley, but we hope to get him back here at the end of March, and he will be working on the twins data analysis. We also have quite a bit of undergraduate involvement. So I'm at Black Hills State University, which is a small liberal arts university, and we really put an emphasis on undergraduate research. And so since the BHUC has been operational, 39 different students have worked at the BHUC during that time. Additionally, we also have a BHSU SURF RU program, which started in the summer of 2016. And since that time, we've had 6 to 8 students this summer come work with us for 10 weeks. And so we've had 66 students since 2016 that have worked on different underground science projects, not necessarily at the BHUC, but could be biology or chemistry projects as well. BHUC future plans, we continue. I think one of the strengths of the BHUC is that we provide reliable, readily available assays to anyone. Anyone can contact us, and we can get an assay in pretty quickly usually, and we have a very good track record since 2015 of providing these assays. We want to increase the sensitivity of our current capabilities by using these dual crystal systems with the twins and Rhyme and Reason. I'm always hoping to get more germanium detectors. And right now, one of the big things that we're interested in is participating in a worldwide counting consortium. So this is related to the XLZD Generation 3 dark matter experiment. And we have a sample that is kind of a lower background sample and one that's a little bit more hotter that's being sent around to low background counting facilities across the world. And we're excited to see the results from those. From that scheme, and I just wanted to emphasize that while our low background counters were very LZ centric because that's who was sending us so many samples during that time frame, we are open to any sample that folks will send us. So we're open for counting samples, but then also we have space. So we have pretty special, pretty unique space in a clean room a mile underground. So that's hard to come by. And so you can see we have this space here. And then we also have space in the biology side and outside the clean room as well. So it's not a clean room environment, but it's still cleaner than a drift. Right now we have two interested parties, I guess we should say. One is the Nemesis detector, which is looking for WIMP annihilation in lead, actually. And they're thinking about moving in within the year. They're moving in a prototype within the year. And then G-STAR, which is a planned low mass dark matter search using germanium, which is funded with an NSF EPSCoR eRISE grant. But we're always interested to talk to folks and see if there might be others as well. So that's all I had. I want to thank you for listening, and I want to thank SURF and the SURF Institute again for inviting me. And I'm ready for questions.
Thank you, Dr. Mount. That was a great update on the Black Hills State University underground campus. I enjoyed the history journey from the humble beginnings through character building opportunities with your students, moving lots of lead, and the bright future for that facility in attracting additional counters or other science as well. Let's open it up for questions. Are there questions online? Let's see. Raise your hand in Zoom and we can unmute you. Go ahead. Let's ask, had Chad Ronish ask a question. Go ahead, Chad.
Good morning. Can you hear me?
Yep.
All right,
Yes.
perfect. Dr. Mountain, curious on the spectrum that you showed out, the peaks that show each individual isotope. How do you determine which isotope is giving you your peaks so that you can identify them?
Yeah, so I guess there's a kind of couple ways to answer that. One way is that we have our calibration sample, and so folks have been looking at these particular peaks for a long time, and when we have a sample, we actually need to match it to the background to make sure we are looking at the peaks we are looking at, and to set the energy scale for the x-axis here as well. But theoretical calculations might be another answer. These decays are determined by nuclear decays, and so you can calculate them. But then also, day to day, what we do is we use our Table Mountain latite calibration sample.
Okay. There's a question in the Q&A from Clayton asking about the materials used in the low background counters. Any special steel, lead, any of the electroformed copper?
Yeah, unfortunately, we don't have any electroformed copper in our detectors. We do have kind of the next best thing that you can buy, which is oxygen-free high conductivity copper. So it is, I think, the purest copper that you can buy. The lead is kind of an interesting discussion too. So we have different types of lead in our shields, and some is better than others. So probably the best lead that we have is what we call old German lead, which I believe was in a basement and found in a basement in Germany because it had been underground for a little while. So it was not cosmogenically activated on the surface. We also have a dough-run lead in our detectors, which is from a lead mine that's known to have lead with low amounts of uranium and thorium potassium as well. And so what we do for a lot of our shields is actually use a graded approach. And so we use kind of our best lead in the middle, and then further out we might use less, not hot, but less good lead, I guess you can say. And in fact, when we're designing our shields, let me see if I can find there we go. So when we're designing our shields, actually, Katie Pedno, the past couple of weeks has been working on developing Merlin shield, because I think in Merlin shield we have 4 different types of lead, and these shields have to be, you do put a bit of thought into the way you stack the lead in these shields. So it's hard to see here, but the goal is that not to have line of sight to the detector through the lead, so you can see the lead here is staggered. And so a big thank you to Katie for figuring out the Merlin stack.
Yeah, some of the other underground labs around the world use some Roman lead. It's been recovered from shipwrecks in the Mediterranean, for instance. So a fabulous connection between cutting edge physics and history. So being put to good service. Another question in the Q&A section talks or asks about the samples that have been counted in the Black Hills State University underground campus. Maybe just comment on what experiments at SURF and maybe beyond SURF. And then a specific question about whether the electroformed copper for the Majorana demonstrator, if that was able to be counted in the facility.
Yes, let me get to my little list here. There we go. So as far as I know, we have not counted the electroformed copper. I think it's honestly below our sensitivity limits. And so the electroformed copper, I believe Pacific Northwest National Lab has put a considerable amount of time into developing procedures to analyze the copper very carefully using ICP-MS. And so the ICP-MS part is pretty simple. It's a mass spectrometer where you have a liquid sample that you make an aerosol and then send it through, and then ionize it, send it through a magnet, and then see how your different isotopes spin with their mass to charge ratio in that magnetic field. And that takes like a minute for an ICP-MS to do. But the problem with the difficult thing with ICP-MS is actually preparing the sample. And so I think PNNL put quite a bit of effort into that electroformed copper analysis.
Yeah, that's absolutely right. If I remember correctly, the level of impurity for the electroformed copper is on the order of parts per quadrillion, and the low background countering technology using germanium is closer to parts per billion, maybe down to parts per trillion in some of the dual crystal systems that you're wanting to bring online. So that's different techniques, and you're right. I think it was an entire R&D project to measure the purity of that copper. It was not an easy endeavor. Other questions that folks have? Raise your hand in Zoom to ask, or put it in the Q&A. Make sure there's nothing that I'm missing there. Maybe I'll ask a general question while we're waiting for others. You called out a lot of student help throughout the entire process. I wonder if you want to say more about the opportunities that Black Hills State University provides for students, and why the low background counting facility is a great introduction.
Yeah, thank you. Of course, I will talk about undergraduates all day. Yeah, so I think low background counting is a really good entrance to physics. It's very accessible. A student can do it with maybe a week or two of some reading and a little bit of training, and they can put a sample in a counter, get the data, and work with it almost immediately. And so it's a wonderful entrance to physics research. And at Black Hills State University, since we're an undergraduate institution, I have the opportunity to work with some really wonderful students. And I think at BH, we do a really good job of kind of shepherding those students to different opportunities, and making sure anybody that wants to research with us underground at the BHUC has that opportunity to come underground. And what a unique place, right? And so I think a lot of folks in South Dakota don't realize necessarily what they have here. And so when we get their students, they're very excited to come a mile underground and work and get that experience. And they've been very successful because of that experience with grad school applications. and doing well in grad school as well. And it's kind of, there's some cool stories too, because you have students whose grandfather has worked at Homestake Mine or something like that. And so there's a lot of history with those students as well.
Great. Other questions from the audience here? Either raise your hand or use the Q&A. Yep, go ahead, Kevin Lesko. Go ahead, Kevin.
Oh, okay, thank you. Had to get unmuted here. I think Brianna is being much too modest about the import of the BHUC on LZ. That the experiment achieved a reduction of a factor of 60 in intrinsic backgrounds. And that was from counting basically every single element of LZ at one time or another. And that wouldn't have happened without her oversight and the commitment of SURF personnel and all of the students she's got to put all those samples in, keep records of everything that was assayed, and assemble an absolutely impressive background model for LZ. So just to highlight the importance of something which looks like sort of routine nuclear physics, this is what enables world-leading research in rare search experiments, underground experiments. So Brianna, thank you for all you've done to help LZ go forward.
Oh, well, thanks, Kevin. It was a pleasure. Thank you for all the work that you've done with Berkeley facility.
Yeah, I certainly echo what Kevin said. It's behind the scenes to a certain extent, but it makes these low background experiments really shine. Another question in the Q&A noted the bend in one of the doors and asking about whether that affects the data or the counts collected.
The bend in one of the dewars.
I think it's the cold finger, maybe the geometries. Oh,
okay. It's kind of just depends on your shield. I don't think you know, that we buy these from Ortec. Can't find a good picture right now of the different bending. Where was the twins? In particular, the twins has two different types of crystals that have cold fingers. I don't think that has anything to do with sensitivity. It's more the samples that you plan to count and how you would like to load those samples. And so some of ours are straight. I can't find the twins to save my life. Oh, there we go. Oh, you can't see it. So, well, yeah, okay. So here is the bend for one of the detectors. So this is the HPGe configuration, and then we have the straight lurker as well. And I suspect, I'm not actually quite sure why this was chosen instead of, I would suspect it's space saving instead of having another straight looker there. But it's just a different way that you can buy the crystal housing in cold finger.
All right. We're almost ready to wrap up, but let me check to see if there are any last questions from the audience here. Well, if not, let's go ahead and, well, thank you again, Dr. Mount. And then to the audience, a reminder that today's talk will be available to view and share on the institute.surf/deeper-talks website, as well as our YouTube and Vimeo channels. Now, next month, we are very excited to relaunch this series as the John Bacall Colloquium, honoring Dr. John Bacall's work on the Standard Solar Model and the solar neutrino problem, as well as his lasting impact on SURF and generations of scientists through mentorship. A special hybrid kickoff event will be held Tuesday, March 10 at 5 p.m. Mountain for those joining in person, and at 6 p.m. for those joining us virtually. The presentation, John Bacall, the godfather of solar neutrinos, will feature distinguished guest Dr. Netta Bacall. More details are available at institute.surf/JBC. And as a reminder, please join us on Slack right after this presentation to continue the conversation with Dr. Mount and others. The link is in the chat. Finally, we value your feedback. Please take a moment to complete the short survey you will receive in Zoom and by email. Your suggestions on future speakers and topics help ensure that this series remains relevant and useful to the community. Thank you all for joining us today.